So, good morning. Welcome to the fifth lecture on the course Applied Electromagnetics. Today we are going to talk about spherical polar coordinate system. Okay, in yesterday's class we talked about the orthogonal coordinate system, which is in general, which has it has a lot of coordinate systems can fit into orthogonal coordinate system. It is a very common name. Orthogonal coordinate system is one in which the coordinates are mutually perpendicular. Okay, rectangular coordinate system or Cartesian coordinate system, they are also the orthogonal coordinate system, and also we have the cylindrical coordinate system and spherical polar coordinate system that we are going to see in this class. So there are other coordinate systems which are also can be put into the group of orthogonal coordinate system. We are not going to learn about those systems like elliptical or conical, things of that nature. So it is suffice for this course to learn about cylindrical coordinate system and spherical polar coordinate system. Those who are interested to do higher level research, they can learn that, okay, using the fundamentals gained from this course. So what is the spherical coordinate system? We are going to talk about it in this class, and then like yesterday's class, we are going to study about the fundamental definitions. Okay, for any point to be described in three-dimensional space, you need three coordinates. What are those three coordinates as in spherical polar coordinate system? That is what we are going to talk about, and then why spherical polar coordinate system is required. And we had already explained that in case of symmetries which have like charge configuration, having charge configuration in spherical symmetry, we will rather employ spherical coordinate system than using a Cartesian coordinate system. If it is a perfect cubical symmetry, then we can use the rectangular coordinate system because it is easy to operate. So certain problems which appear complicated in electromagnetics, they can be best solved by a suitable coordinate system, orthogonal coordinate system. Like for example, if I want to compute electric field or electric potential or magnetic field or magnetic vector potential, then and produced by charge or current configurations which are in spherical symmetry, then I will rather employ a spherical polar coordinate system, and things will be very easier to tackle problems in that manner. We will be exemplifying such stuff when we talk about electrostatics and magnetostatics. For now, you take it for granted that that is the case. Now, having said the purpose of the spherical polar coordinate system, we will talk about, first of all, what are those three coordinates. Again, when we talk about a physical function such as electric field or magnetic field, which have to be, and we have to use vectorial concepts, then we need to bring in the respective vectors in the respective coordinate system into play. So therefore, we need to describe in terms of the vector functions written in those respective coordinates. Therefore, we require to learn about point transformation and vector transformation. And then we will have little bit of classroom activity through demonstration of a few fundamental problems, and more problems will be posted through assignment, and you will all be required to submit the assignments in the same manner that you did in the last time. So what are the coordinates in spherical coordinates system? First of all, imagine a sphere. Imagine a sphere. I want to reach any point on the sphere. Okay, if I want to reach any point on the sphere, I can move along the radial direction of the sphere. So that will be my first coordinate. Okay, then the second coordinate is going to be the theta as mentioned here. The theta is the angle that this radial function makes. So this is the point over here, the green color point which is shown as point r theta phi. So r is the radial distance or the radial vector to the point from the origin, and then theta is the polar angle defined as the angle made by this radial vector with the z-axis. Now, if I project this radial vector onto xy plane, and then I get the angle phi over here, the azimuthal angle, that is the angle that the x-axis makes with the radial vector. So the arrows over here is going to be, actually the arrows over here is going to be along the increasing direction of the values of these coordinates, which means theta is increasing from, so any point located on z-axis, for example, any point located on z-axis is going to be having an angle 0 for theta, but as it goes, it will go up to here. So positive z-axis to negative z-axis, the phi as usual goes around here. So with these three coordinates, I can reach any point on the sphere. Okay, so that is what r theta phi. Let us look at it little deeply, what I said. So this is my rectangular coordinate system. I am going to draw an octant. Octant is 1/8 of a sphere, and superimpose on this Cartesian coordinate system as shown here. Now I want to reach this point P over here at some point on this sphere. So that is the point P, which is marked by this red color. Now I move along this direction, radial direction, or the radial vector makes an angle theta here. Now I drop the perpendicular onto the xy plane and take the projection as shown here, which is going to be the, and that projection makes an angle, or the x-axis makes an angle rather, with this projection as phi. So theta is the polar angle, phi is the azimuthal angle, and r is the radial vector. So this point P can be referred as this, and this point can be visualized in their equivalent. The point remains the same. It is either represented in spherical coordinate system or it is represented in XYZ. Okay, the unit vectors coming along the direction, the unit vectors as usual point along the increasing direction of these respective values as shown in this figure. So the theta goes like this, theta is increasing in this arrow, and phi. And remember, these three unit vectors are mutually perpendicular. Therefore, spherical polar coordinate system is also a subset of orthogonal coordinate system. So that is what it is. Now, what are the properties? Properties are the unit vectors are mutually perpendicular to each other. Okay, that is number one. Then there is, you can see that in a rectangular coordinate system, we had all the three x, y, z. All those three axes are mutually perpendicular. Therefore, to reach any point, we need three linear parameters, namely x, y, z, only length represented. But in case of cylindrical geometry that we saw in the last class, we need two linear parameters, namely any cylinder, you can reach any point on the cylindrical surface by having just one angular parameter and two linear parameters. The two linear parameters in cylindrical symmetry correspond to the radial direction and the along the length, the height of the cylinder. Now, the phi is the angle that is in the azimuthal plane, and that is 360 degree, that you see it here. And then so we have two angular parameters, but in case of sphere you need two angular parameters. One is the theta, the other is the phi. So that the height is not there because anyway it is all radial direction is, it is like isotropic. Anywhere you direct, you can go along radial direction. But you need three things. One is the theta, the other is the phi, then the radial. Okay, radial is the linear parameter measured in meters. The angles, you have to convert it into radians as expected. Okay, so if you use the appropriate units, consistency is the call of the hour. Now, the directions are, as I said, are of these unit vectors. point along the increasing values of these directions, and the unit vectors as usual are not constant in space. They vary with respect to the point in space. Okay, as shown here in this exemplification, the dot product relationship between the unit vectors are a consequence of the the definition of dot product itself, because any dot product between two vectors you have between a and b, for example, is mod a mod b cosine of the angle between them. The angle between the unit vectors are 90 degree, so cos 90 is 0. Therefore, the dot product vanishes between mutually perpendicular directions, and the dot product taken on a unit vector upon itself is going to be 1, because the cosine 0 is 1. Okay, so the 2 points over here are shown here with the red color and the green color, and you can see the directions of these 3 unit vectors are shown here, and you can see that the AR which was pointing over here is not the same as the AR here, this point over here. So it depends on where, as you traverse through the sphere, depending on the point where you are located, the unit vectors are going to vary. However, the unit vectors will be mutually perpendicular. There is no change there. Okay, and because of this, there is an important consequence. We'll come to that probably in the next class when we talk about differential elements, and when we come across this vector calculus, we cannot take these unit vectors outside the integral or outside the differentiation. They are differentiable because they are changing. Okay, with respect to other coordinates, we'll discuss later. Now, point transformation, we can easily see that this is a point on Cartesian coordinate system, because I always bring up this Cartesian coordinate system because it is easy to imagine from the room you are sitting. You look at one corner of your room and all of the 3 walls, okay, all the xy plane, yz plane, zx plane in mutually perpendicular direction, and you take that origin and then you locate a point in space. You can imagine that sitting in your room from where you are listening to this lecture, and this is the point P and r theta. So you know this now very well, and so I am drawing it very quickly. The projection obviously is going to be r sin theta here. In case of cylindrical coordinate system, it was the same radius that is being projected on the xy plane. The rho remains the rho, but in case of spherical coordinate system, this is the biggest difference. The radial vector in space, when it is projected on xy plane, you have to take the component on the xy plane, that will be r sin theta. Okay, so because you have to imagine, that is what I am saying. This will come to that diagram. Okay, so these are the xy. So 3 coordinates can be written as y equal to r sin theta sin phi, and x equal to, so this is my x length. Okay, so let me see where my this is my x length and this is my y length. So I have the x, y, z can be, the z is nothing but the r cos theta. Z is nothing but r cos theta. So we can write the equivalent representation of these points as x equal to r sin theta cos phi, y equal to r sin theta sin phi, and z equal to r cos theta. And having said that, if I want to reverse this, knowing, for example, if I know x, y, z and I want to know the equivalent representation in r theta phi, then this is how it is computed. The second one, r equal to square root of x square plus y square plus z square. You can sum it up. You can put these 3 equations and square these equations, add it up. You will get, because here it will become, if I add x square and y square, it becomes r square sin square theta, and the z square, if I add to that, then it becomes r square. I can take it out, sin square theta plus cos square theta, it will become 1. Therefore, r equal to square root of x square plus y square plus z square, and theta is nothing but the cos inverse of z by r, but I do not know what is r. So therefore, I can substitute the value of r, finding like this, or alternatively, I do not know. So if I know, so that is one way, z by, I can write this r value over here. Alternatively, I can also do another way. If I divide equation sum of this, if I sum up this, I will get actually r square sin square theta equal to square root of x, r square sin square theta equal to x square plus y square. R sin theta will be square root of x square plus y square, and then if I divide those two equations, I will end up getting in tan theta form. Tan theta will be square root of x square plus y square root of x square plus y square divided by z. So that is how it is written. So the r is being removed because we do not know. So these are the three formulas which connect. If I knowing the Cartesian coordinate, I can get the point transformation r theta phi in spherical polar coordinate system. Okay, so how do we use this is something that we will learn throughout this course. So right now you need to understand how the point transformation is done. That has been done already. Now what are the interrelationship? So we know rectangular coordinate system or the Cartesian coordinate system uses xyz, spherical polar coordinate system uses r theta phi, and the cylindrical coordinate system uses rho phi c. And I have brought up the schematic once again so that you don't have to break your brain here for imagination. So you can see that in cylindrical coordinate system, this was my radial vector. So rho will become obviously r sin theta, and the theta, the point equivalent points being r theta phi xyz and rho phi z. So rho is r sin theta. What you must understand is the z in Cartesian coordinate system and cylindrical coordinate system, they remain the same. Similarly, if I compare the cylindrical coordinate system with the spherical polar coordinate system, the phi, the azimuthal angle, is still defined the same. But only difference is the azimuthal angle is taken with respect to the r sin theta in case of spherical coordinate system. In case of the cylindrical coordinate system, it is taken with rho. Okay, but if I employ this relationship properly, then I think I will get the right answer and consistent answer, which will be unique. So this is the way it is. All right. So this is the interrelationship between the points in the three coordinates. It is. It depends on the visualization of the problem, in which see, these are all. It is like a mathematical tool. It's a mathematical weapon in your hand that you are going to employ in solving field problems in for magnetostatics and electrostatics. Okay. Now, given this, I have this. This also the vector transformation. I have just brought all these concepts in the last class. So I am just going to tell you, if I write the vector in Cartesian coordinate, you know it how to write it. The equivalent vector in spherical is going to be along the components along the r direction, theta direction, and phi direction, such as AR, A theta, and A phi. So these three are the components along AR direction, A theta direction, A phi direction, and so that is the analogous terms. And then the unit vectors AX, AY, AC hats, the equivalent of that in spherical system will be AR hat, A theta hat, A phi hat, and we can actually because these unit vectors being mutually perpendicular to each other, we can easily write these components. We can express the components in terms of the dot product with the corresponding unit vectors as mentioned here. Okay, these two last two boxes. Okay, the left and right in the two columns. Now, how do I determine the components in spherical polar coordinate system, RCS coordinate system? This is how it is done. So I pull up that scalar product relationship with the unit vectors. Once I do that, what I'm going to do is the mathematical jugglery I'm going to employ, because the point is the same. So therefore, I can write the vector A either in terms of the Cartesian coordinate system or in terms of the spherical polar coordinate system. Therefore, I'm going to write this vector A over here. This vector A will be represented, will be written in terms of the knowing. Suppose I have a physical function such as electric field in Cartesian coordinate system. I want to, and I find that it is easier to solve the problem in spherical polar coordinate system. What I need to do is, first I need to rewrite the Cartesian coordinate function in terms of the spherical polar coordinate function. To do that, the procedure adopted is going to be explained here. So this is the procedure it is adopted. So since the given function is in Cartesian coordinate system, I will substitute that and I will get this equation 1 as AR equal to AX hat plus AY hat plus AC hat dotted with AR hat. And similarly, I can write for the other two components A theta and A phi as mentioned in equation 2 and equation 3 here. Once I have that, all these three equations can be combined in terms of a matrix form as such. So again, we are getting the three components out of the three components which we know. So the R theta phi components are not known. What we know is Ax, Ay, Ac. For example, given a vector as 5 Ax hat plus 3 Ay hat plus 4 Az hat, then I know that, sorry, 5 Ax hat plus 3 Ay hat plus 5 Az hat. So I know the component along x, y, z direction as 5, 3, 4. So which means I will substitute over here 5, 3, 4. And if I know the dot product relationship between the unit vectors in the two coordinate system, then I can actually get the components in r theta phi in this form, in this fashion. And here is how it is done. Okay, so we are going to take the geometrical construction of these unit vectors, in what angles they look like, and then we are going to pull up those relationship from the geometrical constructions of these unit vectors, as will be exemplified shortly. So this matrix is known as the dot product matrix, or also known as the transformation matrix, which helps us to transform the vector from one coordinate system to the other coordinate system. So we know that the mutually perpendicular things in the three relationship, we know it already. So I'm just going to pull up those relationship over here, and these are the relationship which I'm sure you are seeing it on screen. And because I have shared this PowerPoint already, so it is straightforward. There is no magic over there. So again, I rewrite these equations as I told you. To determine this dot product matrix, we are going to use this geometrical construction. So instead of going back and forth between the slides, I have pulled the already whatever I have explained to you. So the same concepts I have pulled in here. Okay, so the unit vectors in the along the three directions are shown. The Ax and Ay hat is going to be over here. The Ax is along x-axis, Ay is along y-axis, Az is along z-axis. Now I have to take the projection of these vectors on this. Because these are unit vectors, the magnitude of the unit vectors, we know that they are all length. So the only I need to do is the cosine of the angle between the unit vectors, then I get the answer correct. So I want you to pay attention to the, we have to identify the components which are easy. So as I see it, the first component I identified is very easy. The AR vector is along this direction, AC vector is along this direction. The angle between these two unit vectors is going to be theta, which means I am going to get cos theta over here. I don't think there is any big deal about it. Okay, and then you talk about the next one we talk about is the, so that is what is written here, is this the third row over here highlighted by this circle elliptical this thing orbit. So I have highlighted it. So how do I pull up this? Ax, A phi hat. So I am going to draw that diagram in the xy plane. Once I draw this xy plane, I am going to get the angle phi is the azimuthal angle that makes the projection vector or sin theta, and then the direction of this is shown here. Okay, so once having written that, you can see that this Ax is going to be making an angle with A phi, as actually you can see that A phi and this vector is going to be 90 degree. Therefore, this point, okay, this point is going to be phi only. Okay, this very clear. A phi direction is making an angle phi with y-axis is very clear, evident, because this angle is 90 degree, this angle is 90 degree. So this is 90 minus phi. So this must be phi. And then once I have that as phi, then I am going to have that relationship as Ax A phi is going to be cos phi, Ax minus sin phi, sorry about it, Ax hat dotted with A phi dot hat is going to be cos of 90 plus phi, and that will be minus sin phi, and Ay A phi is going to be obviously the straightforward relationship. So I have identified this component as cos theta, this component as minus sin phi, this component as this dot product relationship as cos phi. So all I need to do is, what is AC Fi? Because I told you in cylindrical coordinate system, we have phi and z are perpendicular. So must be the case over here, because phi is an angle that is azimuthal plane in azimuthal plane, whereas c is perpendicular to xy plane. Therefore, the cosine of the angle 90 degree between them is going to be 0. So that component is going to be vanishing. So that is 0. So it is an obvious relationship. Now AC A theta is the only thing that is pending. I want you to pay attention to this carefully. The A theta direction is basically, it is getting beneath the xy plane. Okay, so this one is like 90 degree, and this angle is going to be theta, and this A phi and A theta are making an angle 90 degree, because these are unit vectors in spherical polar coordinate system. They are mutually perpendicular. Therefore, this angle with the xy plane is going to be theta. So this is going to be 90 plus theta. Therefore, it is going to be AC hat dotted with A theta hat will be mod AC mod A theta hat cosine of 90 plus theta, which is going to be minus sin theta. Okay, so that is how it is being pulled up. So these relationships are crystal clear. Any doubt on this will be tackled after the class is over. I can go on a individual attention, and if any one of you has a doubt on how this relationship came, it is straightforward. If you understand the trigonometric and coordinate geometry, I don't think it is rocket science. Now there are 4 elements that we have not found. Let us try to again construct the geometrical figure for those elements. I rewrite this dot product matrix as this way, because I have found some of this, the third column and third row. So I have written those components over here. So those components have been written as you can see on the screen. Now, so to pull out this relationship between AC hat dotted with AR hat, AX hat dotted with AR hat, all I need to do is, I know AX hat is along this direction. What is the direction of AR hat? AR hat is in a 3-dimensional plane. It is along the radial direction. This is not the radial direction of the sphere. So because my point was over there. So remember this figure over here. The point was hanging in space over here. So I cannot put that point as this point. Okay, so do not write this direction as this thing. Rather, it is a projection of R in xy plane, which will be R sin theta. So already there is a projection of sin theta in that xy plane. So I have to first take with the projection with the xy plane, and then I have to again take. So it is akin to taking 2 dot products over there. So when I do that, I am going to get slightly different. How different it is will be shortly understood. So this is the diagram which we know already. So how do I do that? So this is my sin theta over here. My vector is in this plane. So I have to take that projection over here, sin theta. That sin theta is the one that makes an angle phi with the x-axis or ax, because dot product is commutative. So I can either do ax hat with ar hat or ar hat with ax hat. Both are one and the same. Therefore, I say that this phi angle I have put here with ax hat with this sin theta. So it is going to be that sin theta is a projection of the radial vector on xy plane. So sin theta is going to come, and then it is projection of projection, which means it is going to be sin theta cos phi. Okay, so that is the thing. Sin theta cos phi is the projection of projection. Okay, on xy plane. Similarly, ay ar hat, you can easily see it is again sin theta. So this is 90 minus phi, which means sin theta with this ay will be sin theta, and then you will have this. So again projection of projection. So once I do that, it becomes sin theta sin phi. So these two things are pulled out, and then now the leftovers are ax hat, a theta hat, ay hat, a theta hat. If I have to do that, all I need to do, remember the theta is like, it is like this. I have the z-axis, theta is coming in this direction. It is, my xy plane is here, theta is here. My xy plane is, you can see my hand here in my image, and then the theta angle is, the z direction is here. This is my xy plane. So this is the z-axis perpendicular to xy plane. The theta is an angle that the radial vector points in this direction. It is increasing along this direction. So which means theta is going to be along this. So theta is like this. Again, I have to take the projection of this on xy plane. To do that, I have to pull this relationship. This becomes actually little bit. It becomes cos theta because the theta, these mutually perpendicular directions. So if I want you to imagine in xy plane, it is going to make an angle theta because this is theta, this is 90 minus theta, then this is going to be theta, which means in the xy plane, the a theta direction is going to make an cosine of theta, which is therefore the component. So again, it is projection of projection on xy plane. So here it is a projection of cos theta component on ax hat, cos theta component on ay hat. Therefore, ax hat, a theta hat will be cos theta cos phi, while ay hat, a theta hat will be cos theta sin phi, sin phi. Okay, so that is how it is pulled out this relationship. So this is the a theta, the direction that is shown is not, it is getting beneath the xy plane. So that is, you must recognize that fact. Okay, so it is not, a theta direction is not located, it is rather in this, it is not here, a theta is not here, a theta is like this. Okay, so given this, and these are mutually perpendicular direction, this is my radial direction, this is my a theta direction, mutually perpendicular, this makes an angle theta with xy plane 90 minus theta, so this must be making an angle theta. So I am sure that you are seeing my hand, and I think you can see the video once I upload it in YouTube. Again, if you don't understand, and still if you don't understand, you are welcome to come and discuss with me. This is how it is done. So to show that projection clearly, I have marked these projected vectors on xy plane. So I have projected this a theta direction on xy plane with this dotted line, and this is the angle theta. So you can see that clearly. So I want you to take a few seconds and look at this figure and make sure you are able to get all the relationship. Now all the relationships have been eked out. So we will fill up this matrix as like this. Sin theta cos phi, sin theta sin phi, cos theta cos phi, cos theta sin phi, minus sin theta minus sin phi cos phi 0. Okay, so once I get this transformation matrix, then I can write these components easily like this. So I am only rewriting those things just to for you to make easy attention to the screen rather than going back and forth on the screen. Okay, which is really cumbersome and uneasy. So once I have that, I get this. So I can get these components from this matrix, and then I can visualize the vector in spherical polar coordinate system by substituting the components after multiplying the respective things. Like I gave you an example, 5ax hat plus 3ay hat plus 4az hat, then it becomes ax becomes capital AX becomes component along the xy direction becomes 5, 3, 4. So once I substitute here, and I can operate that at any given angle and get the AR and A theta A phi, and I can substitute those and get the vector representation written in spherical polar coordinate system. And once I do that, I can, now the only thing is this matrix is applicable when I know the rectangular coordinate system components and I want to do it. Now if I have to do the reverse, okay, if I have to do the reverse, that is knowing spherical coordinate system, I am having a perfect cubical symmetry, but my given vector function is in spherical coordinate system. It is easy to tackle such problems in a perpendicular, the rectangular coordinate system, okay, where all the three axes are linear, and then I can do it in rectangular coordinate system. If I have to do that, I have to transform the given vector in spherical coordinate system to rectangular coordinate system. So all I need to do is take the inverse of the transformation matrix that we just did it, and we can rewrite like this and get the dot product stable like this and get this dot product matrix as mentioned here. Okay, so what I have done here, you can see that identify. I have taken the three components with respect to the, so I have done the mathematical jugglery in a reverse fashion now. Knowing the AR, A theta, A phi component, I have to take it along the XY direction. So which means I have given vector is in spherical polar coordinate system. So I write the transformation matrix in this form. And what are we see, what you are seeing is the diagonal elements are not changing, only the other elements are changing. So please pay attention. What I want you to do right now is basically, not right now, maybe after the class, you can take a piece of paper and try to visualize the things like taught in the class, and take a pen and a paper and redraw the diagram the way I have explained, and try to visualize. Until and unless you do that, you cannot get it completely right. Okay, so there is a little bit of homework for you for the day, which you can do it on your own, and try to get this reverse transformation matrix by doing it and visualizing the component in the same form. So you can see that these components have switched. The same thing with these two components, it has switched over here. So you can see that, compare the two dot product matrix, you can see what I'm trying to say here. Okay, you can realize. Okay, it is all very fundamental vector algebra that we have taken use of it. That is why I said vector algebra, when you talk about vectors, yeah, I know these components x, y, z, and similarly I know what is a dot product, what is a cross product, I know what is a triple product, what is a scalar product. But when I want to put these vector concepts in a different coordinate system, you can see the projection come into play. So vector projection is what you must learn. Okay, if I know the vector projection, here the vector projection is all related to the unit vectors. Therefore, we don't care about the magnitude, because all of the magnitudes of all of these unit vectors is going to be actually 1. Therefore, you are getting this relationship as shown here. So you can get this. I am sure that you have learned this spherical polar coordinate system. I am going to upload the video right after this class. You can go through the video once or twice, and then as I told you, try to take a piece of paper and try to do the same mathematics on your own, and try to compare this transformation matrix shown in the class with what you are doing, and then if you find identical, that means your understanding is perfect. Until you get that identical understanding, you keep knocking at it. Okay, at some point you will get it. Okay, thank you. So let us talk about these 3 problems in this class. Just a second. So we are going to